Good day to you all. It's Evan Snyman here for 1.10 Making the Difference. We're doing today the first lesson on analytical geometry, and we're going to be doing some revision of the grade 11 content. Okay, so for me, we need to know the formulae, and I know the formulae are given to you on the formula sheet, but I prefer my students to know the formulae off by heart because it just makes sense to do so. So what I'd like to look at now is if the gradient is y2 minus y1 over x2 minus x1. I like my kids to realize that actually what we're talking about here is a triangle that is based on the horizontal and vertical components, where this idea is y2 minus y1, and this is the idea of x2 minus x1, albeit that we're talking about yb minus ya and xb minus xa in this example. In other words, this vertical component is the change in y, and this horizontal component is the change in x. So you can do it by substituting things into the formula and saying, cool, this is 4 minus 3. Sorry, I'm going to fix that. I know I've made a mistake here already. So we need to go back and fix that. It is 1 minus 3. So again, it is that easy. Even though this is quite one of the easier topics of paper 2, it is very easy to make careless errors here, which is one of the things I'm trying to avoid by what I'm going to advise you. 4 minus 5. So we're going to get an answer here of 1 minus 3, 2 minus, so we know that that's going to be 4, and we know that 4 minus 5 is 9. The gradient here is going to be 4 over 9. I actually prefer to do this slightly differently. And that is to say, just to use a much more intuitive idea of the idea of, well, what if you were one floor above ground? Because that is what a y value of 1 means. It means it's one unit above the x-axis. So if I was sitting here with something that was 1 unit above the x-axis and going down to something that was 3 units below the x-axis, I would know that that distance there was 4. In the same way, if I was dealing with something that is in the position of minus 5 on the x-axis, I would know that it would take me 5 units to get across to the y-axis. And if I had a value of 4 on the as my x value over here for b, I would know that it would take me further 4 units to go to the right to get to be in line with b, which means that my movement in the x-axis, my horizontal movement would be 9. And as a result, if I've got this being my change in y and this being my change in x, I can get there that this is going to be 4 over 9 by a quick diagram, by quickly inserting things on the diagram. Now, I won't lie to you, I like this idea because just as easily I can get my distance formula from here. My distance is given as the square root of x2 minus x1 squared plus y2 minus y1 squared. And you would do the same sort of thing as before, where you're doing a lot of substitutions. What I don't like about this method that we're doing here is far too many times my pupils have made errors with minus signs. And so what they do is they say, cool, we're going to have 4 minus 5 squared plus 1 minus 3 squared. And I've left a bracket out, it's already wrong. So it's going to be 9 squared plus 4 squared equals 81 plus 16 equals the square root of 97. I know that it might not be the standard method, but I much prefer to see my students realizing that this same idea can be used for distance formula. That effectively, what we're talking about here is the change in x squared plus the change in y squared. So I could say that this is going to be immediately 9 squared plus 4 squared equals 81 plus 16 equals the square root of 97. I think that is a lot faster. And if you understand how a gradients formula is constructed, you can use that same idea to develop a slightly faster way to deal with a distance formula. And I would really encourage you to see if what I've been saying here makes sense and see if that helps you get your use your distance. So for me, I would do both the gradient and the distance formula by including a small set of drawing this triangle with the horizontal and vertical components onto my diagram. I also have an alternate way of doing the midpoint midpoint. And again, I know that the formula sheet says it is x1 plus x2 over 2. It is the average of the two values, y1 plus y2 over 2. Again, whereas the other formulas always have y2, then y1, this one has y1, then y2, so the order is transposed. These things can get tricksy. Okay, and again, we are going to do it by substitution. And so we're going to say, cool, this is minus 5 plus 4 over 2, so it's minus a half. And it is going to be minus 3 plus 1 over 2, so it's going to be minus 1. Again, for me, I like a more intuitive idea of saying, well, hold on, where would you expect to find a midpoint? You'd find a midpoint in the middle. So if A's value was minus 5 minus 3, and B's value was 4, 1, then I would say, my idea, my thinking is, well, hold on, to get from minus 3 to 1, you've gone up by 4. So you'd have gone up in 2 steps of 2. And what value is 2 larger than minus 3? It would be a 1, a minus 1. And what value would be alternatively 2 lower if we were going to go backwards from 1? What value would be 2 lower than 1? It would be minus 1. Now, I chose to do the y values there because the answer was a whole number. It is not quite as clear with the in this case with the example I've chosen here with the x values, but the method still works, and that's the key I'd like to show you. So what I'm saying is the change in x here is 9, which means I made 2 steps of 9 over 2 and 9 over 2, because I'm making the midpoint will be halfway along. 9 over 2 is 4.5. So what is 4.5 to the right of minus 5? That would be minus a half. Alternatively, what is 4.5 to the left of 4? Or 4.5 to the left of 4 would be minus a half. So I would encourage you to consider whether using the formulae and doing all the substitutions and making mistakes and risking making mistakes with minus signs is worth it, or whether we can get on and do work without it. I'm now looking at a slightly interesting example. Okay, determine analytically. Now, this problem can be solved using trigonometry. It can be solved by drawing an accurate diagram. It can be solved by simply looking at the picture and saying, I know the answer. But they do say to you, determine analytically. If the largest angle of this triangle is acute, obtuse, or right angled. Now, what I'm going to choose to do here is, I could choose to use gradients. Gradients would tell me if this thing was right angled. We know that if things are right angled, the product of the gradients will be minus 1. Alternatively, the two gradients are negative reciprocals of one another. But that doesn't tell me if they are acute or obtuse angled. And the key there possibly is to look at Pythagoras. Okay, Pythagoras tells you when something is right angled, but those of you who played around with Pythagoras know that it can also be expanded to tell you if things are acute or obtuse. So the hint here is actually in the question that we should probably be looking at Pythagoras. For Pythagoras, I need to know the lengths of the sides. Okay, so what I'm going to do is, as I said to you, I'm going to draw in my triangles. And if I drew in this triangle, it's kind of convenient that this one is on the, this point B is on the on the y-axis. So from -5 across the y-axis, I have changed by 5. To get from this point, from this y value of -3 up to this y value of 2, I've gone up by 5. So for me, the distance of AB is equal to 5 squared plus 5 squared equals the square root of 50. Okay, I'm going to do the same thing because it's working. To find the length of AC, draw in the triangle. From -5 across to 2, the length was 7. From -3 down to -4, the length was 1. So the distance of AC, or the length of AC, is going to be 7 squared plus 1 squared equals the square root of 50. I know I have not simplified this down to 5 roots 2, but I don't need to in this particular example. Okay. Oh, that's interesting. If these two lengths are the same, that does seem to imply that this triangle is isosceles. We will hold our breath. There's a small chance that it might be equilateral. So let's see what happens. From B to C, let's draw in our right-angled triangle. We're going from naught across to, we're going from naught across to 2, so the change in x is 2. We're going from 2 down to -4, so the change in y is 6. So the length of BC is equal to 2 squared plus 6 squared equals the square root of 40. Now, those of you who have drawn this diagram a little bit more accurately than me would have immediately said to you, well, we can see then that this thing must be acute angled. I'd like to just continue with my proof and show you, well, hold on. If this thing is going to be right angled, then the longest side must equal to the sum of the other two sides, or the longest side squared must be equal to the length of the other two sides squared, or the sum of the other two sides squared. So I'm going to try that. And I'm getting 50 squared. Does that equal the other two sides squared and added together? And what I get here is 50 being compared with 90. And the problem here is that it is too small. Now, if it was the right length, we'd know it was going to be a right angled. And since this thing is too small, we know that the side must be shorter than expected, and therefore it must be acute angled. So again, if I was asked to classify this triangle, I could have said that this thing was, hold on, as I said earlier, I can realize that this thing would have been isosceles. Okay, and I know that it is an isosceles acute angled triangle by this idea. So for me, what I'd like to come back to is I would not necessarily rely on always looking up the formulae on the formula sheet. I would learn the formulae off by heart. And what I would really encourage you to do is, if at all possible, use the shortcuts I've tried to show you over here, where understand that y2 minus y1 is the equivalent of the change in y, or effectively the vertical component of that change, and that the x2 minus x1 is the horizontal component of that change, the change in x. I can use it both for the gradient, but I can use it equally easily for the distance formula. And you find a shortened version of the distance formula that I think is more effective because it doesn't rely on substitution, where there are errors to be made with minus signs, the proliferation thereof. And I would encourage you to look at possibly using a slightly different version of finding the midpoint by this idea of intuitively realizing that a midpoint must be in the middle, halfway across the x values and halfway across the y values. Okay, this is the first half of our revision session. There's one more to follow. Hopefully you'll tune in again. All the best.